Today, basically, I will talk about this track selection criteria that we generally used in our analysis, and then I will end with some how I will end with some PID selection, means how we select how we get how it access the PID information from the ESD and AOD files and used it in the analysis. So I will end with that. So before going to the track selection, let me just summarize what we have learned till now. So in the day two, we basically learned how we write a skeleton of analysis task and how we can access the event and track from the AOD and ESD file. So here is basically just a part of the code where we generally do our analysis in this user execution of our .cxx macro, where we uh, get the event information which is stored in this FAOD. One can also do it using the ESD event and stored it in the ESD. Then from there, we just check, we get the number of tracks in that given event. That's basically the multiplicity. Then we do then we did a track loop, and in each track, and for the each of the track, we get the track information from the uh, we get the track information for the corresponding track, and then we basically fill a histogram of any track variable like PT. So in that third day, what we did, we just in after getting the events in the given input file, we use some event selection cart, which basically contains some physics selection, some physics selection, some triggered selection, some pile-up rejection, and vertex selection. And using those cards, we select some good events from the total events, and then we used it further for our analysis. And in order to do so, what we used a class which is called as the Ali event cards, which one can define in the header file. And just one need to check that if the accept means if we have a pointer for the given event, then we need to check that if the event is accepted by this Ali event card or not. If it is accepted, then one can further use it in the analysis, and you from those event one can also extract some event properties like vertex jet condition, like vertex jet condition, which I have shown here. One can do it like this. Now today what we will do, we will put some additional selection criteria, but not in the event level, in the track level, inside this track loop here. And we will further select some good tracks from the available tracks stored for that given event. Now, so first I will start with the ESD track, then I will go to the AOD. So this track selection in ESD for the ESD event or the ESD track, we do using the AliESD track card. So there are some default set of cards which are available for in this class AliESD track cards, which I think is a very good starting point for our analysis. Although depending upon our analysis, one needs to use some additional cut or some stricter condition on the track variable that one can do depending on their analysis. But for the starting point, one can always start with some default cut that is already defined in the LESD track cut. So this cut is basically, there are mainly three type of cut. That is the standard ITS TPC 2010 cut set, standard ITS TPC 2011, and standard ITS TPC 2015 cut set. So the main difference is that between 2010 cut set and 2011 cut set, the main difference is basically the cut of DCA-XY. In the both case, the DCA-XY is PT dependent, but the resolution of the DCA-XY or the impact parameter is different. Therefore, one need to one used we use different boundary for this DCA-XY in these two different cut set. And between 2011 and 2015, the main difference is that in 2015 we use some additional geometrical cut. So throughout this lecture, I will basically concentrate on the 2011 card, which we generally used in run 2 data. Now, how to implement this card? So first one need to get a pointer for this. Get one need to define a one need to define a object for this AliESDtrackCut class. One can do it in our header file, which is the alianalysis mytas.h. You can directly define it in as a private member. Then one need to implement this cut in the analysis my task.cxx, where we generally write our analysis task. So first one need to initialize this FEHD track cut object in our constructor. One can just initialize it in the constructor. Then the main then one need to define this cut, which set of cut he wants to use, 2011 cut or 2010 cut, and if he wants to put some additional kinematic condition like eta and pt, all those things can be done in the user create output object, where we generally define our output object like histogram and tree that we are going to fill our in our output file. So in that section, means in that function of the .cxs class, one can also define this which kind of track selection card he or she is going to use. For example, here I show how one can define it. So we can see that we have the object efsd trackers. Then I just call the get standard its tpc tracker 2011 from this class, which have two argument. One is get true, the first, which is two argument. The first argument is basically gives you the handle over the uh, if you give, it gives you the handle to control the uh, track cards. Means if you used it k true, then it will basically use some default track card, and if you use k false, then you can manually change those track cards. For example, if you have a track variable, say number of cluster of tpc, so by default it is 50, and if you want to change, if you want to put a cut of 70, then you just need to call put here k false, and then you need to call the set number of TPC cluster, and you can put the any number that you want. And the second argument is for the also is also for related to the TPC. So in the track cut, when we use some track cut in the TPC for the track selection, it allows us this which kind of TPC information we are going to use in our analysis. So one can put some cut on the number of TPC cluster to get a set of good track, or one can also put some cut on the number of TPC crossroads. I will come to it later. What is this cluster and crossroads mean in the TPCs for selecting the good set of track cut. So this one corresponding that you are going to use the cut on the TPC crossroads, and if you put here 0, then you will going to use the tracks which is selected upon the cut of TPC cluster. Then one can also put some kinematic range like PT range and eta range of their cut by calling set PT range and set eta range. Here one can see I have put that I will only use those track in my analysis which have some PT from 0.35 to 2 and eta between 0.8 minus 0.8 to 0.8. Then after defining this cut, one can directly check if your track of your selected track in the event loop is past this track cuts set of track cuts, or it is not. If it is passed, then you can use it in analysis, and if it is not, you can just continue. You will not use it in your analysis, and you can do it by just calling the accept track and put the track object that is I have you can see here. For example, ESD, you just put this object in the argument here. Then it will basically return you a boolean number, and by looking at it you can if it is true, then you can use it in your analysis. The track is good track, you select it with some default track selection criteria, and if it is bad, then you can reject it from your analysis. Now let's go to this what are the different kind of track selection that we have in this standard ITS TPC 2011 cut. So I will go one by one. So first set of cut is related to the TPC, which I have just highlighted here. What we have, so you can see here. First, we have the condition that the I mentioned in my earlier slide that in the second argument it basically tells us if we are going to use the cluster cut or the crossroads cut. If we put 0, that will basically use the cluster cut, and for the cluster cut we just use that the minimum number of cluster in the TPC is 50. And if you use 1, then it will use the crossroads cut, which will basically use the minimum number of crossroads 70, and the ratio of crossroads over the findable cluster equal to 0.8. So what is this cluster and crossroads? So from this here you can see what is this cluster and crossroads. So in TPC we have 159 159 pad. We generally called it the rows, and when a track passed through this, so we just check how many means we just check that how many rows this one track passed through. So that is basically the cost rows. And when a track passed, it will basically create some cluster. So that is create some cluster or the space point, that is basically the TPC cluster. So that is basically the cluster. And this cluster and number of crossroads, they may not be same in all the cases. For example, here you can see that we have the 7 crossroads, and when a track passed through this crossroads, we have the 7 rows, and when a track pass through it, so we generally call that we this track pass the 7 crossroads, but it has only the 6 number of cluster or 6 number of data point depending upon the uh, energy deposition and the pixel that it's energy deposition and the sensor that is fired. So this is basically the difference between the TPC cluster and the TPC crossroads. Now we have another condition that uh, that the we fix the maximum number of chi-square per cluster TPC equal to 4. What does this mean? So this TPC is basically used for the tracking. So how we do the tracking? We do the tracking by Kalman filter algorithm, where we fitted the heat in the detector and try to reconstruct a track. And when you do this fitting, you have some chi-square of the fitting. So it's basically the maximum chi-square per cluster. So you extract the maximum, you extract the chi-square from your track fitting in the TPC range. Then you just divided it with the number of cluster. And if the ratio, if the chi-square per cluster is less than 4, then you select that track as a good track. Now let's go to the second another kind of tracker that is we used in this set, that is the set accept king decay daughter. So what is this? So which is set as false, means in this track we will not use the track which are coming from king decay. So what is this king decay? So king decay is a particular topology of decaying of a charge particle into one charge particle and one neutral particle. For example, the kaon going to muon and one muon and one neutrino. So this kaon has a positive charge, muon has a positive charge, and neutrino is a neutral particle. So when we reconstruct the track, we generally assigned a status to the each track, that if the track is coming from the kink or not. And we did it using some kink using some algorithm, that is basically the kink algorithm, which depends on the angle and the energy momentum conservation. For example, say if we have a kaon track which in the TPC fiducial volume which further decays to mu plus and neutrino, then what we will see? We will see that we cannot see this neutrino. We will just see a track coming to the TPC, then it just bend its direction. So basically, there is a we will find that there will be a two positive charge which crosses each other, which will suggest us that this track might be from king, and after that we will use some additional energy momentum conservation and some algorithm to confirm that if the track is coming from kink or not. Then we put a status that if the track is coming from a kink or not. And as in our analysis, we always use the primary tracks. So these kink tracks are not the tracks from the primary particle, from the that are not originating from the primary vertex. That is why in our analysis we always reject this track, that is this kink daughter track, that is basically this muon. Now we have another two condition, that is the we can see here that that is a set required TPC refit and set required ITS refit. So this is basically, and we put it as a K true. So we basically select those track which is uh, uh, which has a successful status when we do the refitting. So what is this refitting? So probably this refitting is related to the tracking, how we do our how we reconstruct our track. Probably this will be this will be discussed in the detector lecture. uh, so how we generally, when we reconstruct the track, we reconstruct it in three different steps. So first step, we reconstruct the track using the heat from the TPC and ITS. We basically we started our fitting from the outer layer of the TPC to the inner layer of the to the inner layer of the ITS. That's called the way in. Means we started our track reconstruction from that TPC outer layer of the TPC to the inner layer of the ITS, and we assign. You can see here we have assigned some point like TPC in and ITS in. So basically, these are the means we stored some track parameter information for uh, at the inner layer of the TPC and the ITS, inner layer of the ITS. Then what we do in the second step, we again started our fitting, but it is in the outward way from the ITS to the outward, like ITS, then TPC, then TRD, then TOF. And in this manner, we also store some track parameter information in each of the detector label, which is known as, and this information is known as the TPC out, ITS out, TRD out, and TOF out. Then again we do another refit from the uh, outermost layer of the TOF to the ITS. So this is called basically the refit. So in the detector for the each track, we basically have some flag which tells us. So you can see here, which tells us that if the track reconstruction or the Kalman algorithm is successful for the detector in that particular step. So and what are the steps? So there are basically three steps: the inward, outward, and refit. The first step, second step, and third step. So this set required TPC refit K true means your track reconstruction is successful for the TPC detector when you do the refitting. Mean the last when you do the refitting in the last stage of the tracking, and similarly also for the ITS. Now there is a another condition, that is the ESD track set maximum chi-square TPC constant global. So this equal to 36. So this condition is also known as is also known as a golden track condition, because using this track selection condition, one can significantly improve the quality of the track. So what this track condition means? This track condition means a chi-square difference between the TPC only track parameters extrapolated to primary vertex and the global track parameters. So if you reconstruct the track only the using only the information of TPC, that calls basically the TPC only track, and the global track is basically when you reconstruct the track using the information of TPC and ITS. And as I mentioned that, and each of the label, we stored some track parameter information. So what is this track parameter information? So we basically store 5 track parameter information. What is Y, Z, sine phi, tan lambda, and 1 by pt. So what is those? Those are basically the local coordinate and the 1 by transverse momentum. So y is basically the local y coordinate of the track. So what is local and global track coordinate? So in your detector system, you will have some global coordinate, x global, y global, and z global. And local is defined when you do the tracking. For example, these are our tracking detector. So it is defined as the local axis, and this phi is basically the and we basically stored the information, that is the x, y, z, in this local coordinate, and also the azimuthal angle, which is basically the azimuthal angle in the with respect to this local x axis. So basically, what we compare, we just calculate the chi-square difference of these parameters for the TPC only track and the global track, and we said if the difference is less than 36, then it is a good track. And in this way, one can remove the fake high PT tracks due to some wrong association of ITS cluster. Now let's come to the track cut on the ITS. So first of all, we used a track cut that the set cluster requirement of the ITS. We used at least one hit in the SPD detector. In this way, one can reduce significantly the tracks that are coming from the out of bunch pileup. So if you put a condition that your tracks should have a hit in the any layer of the SPD, basically SPD has a two layer. If it has any layer of the SPD, then the most probable case is that these tracks are from the actual collision, not from some other pile up collision. Then we put some cut on the impact parameter of the DCA-XY. So the DCA-XY basically is the closest distance between your track and the primary vertex, which is also known as the impact parameter. So we put a cut of 7 sigma, and the sigma is a PT dependent thing, and it varies from the run 1 and run 2. In run 1, this resolution or the sigma of the impact parameter is different compared to run 2. That is why we have the we have two different kind of cut set known as 2010 and 11, just because of this different resolution in these two run. So we basically used a PT dependent DCXY cut, which I shown here. So this cut is basically a 7 sigma cut on the impact parameter resolution. And we also put a cut on the z direction of the impact parameter by amount some 2 centimeter, and also a chi-square cut of the ITS, means when we use the ITS point for the fitting or the Kalman algorithm for the track reconstruction. At that time, we use this chi-square cut of the fitting, that is the maximum chi-square per TPC cluster ITS equal to 36. So one can see that here this number of maximum chi-square is different in case of TPC and ITS. In TPC, it is more small compared to the ITS because the TPC, as I mentioned, that we have 159 crossroads. Therefore, if you do the chi-square per cluster, so the number of cluster is basically high, so the chi-square per cluster is basically low. But in case of ITS, we have only the 6 layer or the 6 seat for the reconstruction. That is why this chi-square cluster per ITS is large in case of ITS. Now, these are basically the set of this ESD track cards that we we used generally in our analysis to get a good primary ESD track. Now let's go to the AOD track. So the AOD track, so this AOD data file is formed, means is it is formed from the ESD data file by using some particular cut set, and this particular cut set is defined by some filter bit or some filter bit mask. So in case of AOD tracks, we always have some filter bit mask which store the information about whether the track satisfies some standard sets of quality criteria. For example, here you can see some bit like bit 0, 1, 2, 3, 4, 6, 7, and all this bit corresponds to a particular set of cut. And we stored all this information, means we if we take a ESD track and then check if it is if it is passed uh, all these if it is passed this this particular set of selection criteria, and depending upon which selection criteria it passed, we assigned a filter, we assigned a bit to the track. For example, if it is passed this first selection criteria, then we assign this bit 0 1, and if it is passed some this criteria, then we'll assign the flag here. In this way, the track in the AOD file, it has this filter bit mask or the information of the filter bit. So one can use this filter bit and check which selection criteria the track is, the track is passed which selection criteria, and accordingly to that one can use it in his analysis. Now here I've showed just a put it just a table to show you what this bit and the cuts means in the filter bit. For example, in this bracket, these are basically known as the filter bit: 001, 002, 004, 008, 64, 128, 32. These are basically the numbers. So you just need to check if your track passed, it means if you want to check that if your track passed the filter bit 128, then it basically what you will check, you will check that if the track passed some particular selection criteria which is defined here. For example, if you take 256 or 32, so the 32 means that it passed a standard ITS TPC tracker 2011 that I have just discussed earlier. And if we take filter bit 256, then it is a in addition to this standard ITS tracker 2011, it has some additional DCA XY, DCA Z, and other condition which is putted here, some different condition. So depending upon this filter bit, one can select their track in the AOD level. And let me show here how one can do it. For example, we have a track loop that I just mentioned in my earlier slide. Then one need to create a object of the AOD track. Then one just to need to check if the filter bit is 128 or 252 or 32, depending which kind of cut set you want to use in your analysis. So if it pass this particular kind of cut that is defined in this filter bit, then you can use it in your analysis. Now one can also do it by just calling the test filter bit mask, but not calling that test filter bit. So what is the test filter bit mask? So this bit 0, bit 1, bit 2 is basically your test filter bit mask, and in the bracket these numbers are basically is your filter bit. So one need to be careful when he or she is going to apply this cut. So you can also just call this filter bit mask and put the corresponding bit number of a filter bit cut. Okay, now so these are basically that event track selection criteria in the ESD and the AOD level. Now let me go to some additional information. Means so first, what we do, we can select some particular track by from this uh, predefined cut selection. Then, if one wants to use some additional stricter cut on some stricter track variable, they can also
Hello.
do.
Uh,
Yes.
Excuse me for just one question. Does the filter bit the cuts which corresponds to a given filter bit? So does it depend on the data set like for
Yeah, it
2000?
depends. It depends on the data set. For that, one can always look at the wiki I have mentioned here.
Okay.
There, they have the information that using which cut set they construct the AOD file. From there, they can find which filter
Okay.
bit corresponds to which
Okay.
cuts. It depends on the data set. Okay. So as I mentioned that one can also add some stricter cut by selecting some track parameters. And here in the next few slides, I will show how one can get some track information in some detector level for some information from the ITS, some information from the TPC. And So let's first start with the ITS. So one can get the number of ITS cluster from the ESD and AOD track by just calling the get ITS number of cluster and get just by calling the get ITS number of cluster. So one need to one need to careful that if he activate this KITS refit, means if you go to this track selection 2011, where we can see that we always make this ITS refit true. That means it will use the cluster of the ITS in the track reconstruction. In that case, we will always have greater than or equal to 2 number of ITS cluster. If we do not put that condition, then we can have maximum 6 number of cluster. And your analysis, you can further put any additional cut that your track needs to have 4 ITS cluster, 1 ITS cluster, 3 ITS cluster, depending upon your criteria. Then you can also check in which layer of the ITS the track has a heat. You can do it by calling the hash point on ITS layer, and in the argument you can put the number of the layer. So it basically gives you a Boolean number, and to basically tell you that if the track has any heat on any particular layer of the ITS. So the number stands for, if you put 0, then it will say if the track has any heat in the inner layer of the SPD. If you put 5, then it will tell you that if it has any heat in the outer layer of the SSD. So in the ITS, we have the 3 detector: SPD, STD, and the SSD. So basically, it's total 3 into 2, 6 heats you can get. Now one can also get the chi-square information from the ITS, from the fitting of the ITS points during the track reconstruction. And you can do it by calling the get ITS chi-square in the both in the ESD and the AOD track, for the both in the ESD and the AOD track. Now let's me go to the TPC, how one can extract some information from the TPC. So one can extract the information of the TPC cluster by calling the get TPC and cluster in the both ITS and in the both ESD and AOD track level. So the number of cluster, you will get basically the number of cluster which is included in the Kalman filter algorithm during the reconstruction of your track. Then you can also call the number of crossroads by, you can also get the number of crossroads by calling get TPC crossroads in both ESD and AOD level. Then you can also find the number of findable cluster, which are with the, what is the number of findable cluster? So it is basically the number of TPC TPC pad rows crossed by the tracks, computed taking into the account of the dead zones on the TPC pad rows. And one can retrieve it by calling the TPC n class F. Uh, and one can also get the information of TPC chi-square fitting by calling the LESD get TPC chi-square. But and also in the case of AOD, one can directly get the TPC chi-square per NDF by just calling the chi-square per NDF. In case of AOD, you cannot get only the TPC chi-square, you can directly get the chi-square per NDF. So it is little bit different compared to the chi-square per TPC cluster, because this NDF is basically 2 into number of cluster minus 5. So in this way, this is basically the TPC chi-square minus TPC chi-square by 2 into number of cluster minus 5. So one need to be careful when he use this ESD and AOD, and if he wants to use any additional cut on this TPC chi-square per cluster. Now let's go how one can also get the information of the momentum and charge and impact parameter. So you can directly get the charge information by just calling that track charge, by just calling the charge. And you can also always get the information of the DCA-XY and DCA-Z by just calling the get impact parameters. And in the argument, you need to pass the some float variable that I have defined here. That is basically DCA-XY and DCA-Z. So the first argument will be filled with the DCA-XY information, and the second argument or the variable will be filled with the DCA-Z information. Now you can also get the information of each component of the momentum like px, py, and pz. For that, you need to define the array of a double. For example, here I have defined its p. Then you can just call track px, py, pz and put the double number in the argument. Then it will basically fill the array with the information of px, py, and pz for a given track. So these are very basic track selection and track variables that one widely used in their analysis. So after that, let's go to the PID information, how one can extract the PID information in our analysis task. So one can extract the PID information using the class LE response. So for that, how one can implement this? So for that, first one, you need to load this LE task PID response.c macro in your steering macro or run plugin.c. Then you can put some condition that depends if are you using this Monte Carlo data or the uh, original data. Then you need to define the object for this at PID response in your header file here. Then you need to de- uh, initialize this object in your two constructor that we have in our analysis mytask.cxx. Then one can use it in the analysis chain. So for that, one first need to define it in the user create output object. One need to do some setup for the particle identification. So how one can do that? One just can do that by just defining a analysis manager. Then from the analysis manager, one can call get the input handler for the analysis. Then from the input handler, one can get the PID response. So this is basically the object of your PID response class. And further, you can use this object to get the information of the PID from the different detector. For example, here I show how one can extract the n sigma of TPC. You just need to call in number of sigmas TPC. Then you need to, in the argument, in the first argument, you need to pass the pointer of your track. And in the second argument, you need to pass the information of the particle, means the n sigma distribution of which particle you want to see, of a proton, kaon, pion, deuteron. You can see any, you can put any of the any particle here. Similarly, you can also extract the n sigma of other detector like TOF, HMPID, and other detector or ITS. And here I just want to mention one thing for those who are doing the nuclei analysis. Uh, just one thing, that when you are in the nuclei analysis, when we means in this analysis track, when we extract the momentum information, so what we do, we generally basically uh, calculate this n sigma distribution. We calculate this n, we do this n sigma distribution in different momentum region. Then we fitted it, and from there we extracted the yield of the primary particle like kaon, proton, and etc. But in the nuclei analysis, when the particle have a charge 2, you just to remember that the LESD track that returns you the, that basically do not returns you the momentum. It basically returns you the momentum by z. So if you are dealing with some particle which have charge 2, in that case you need to multiply with 2 in the momentum level to get the proper momentum. That one thing always need to remember. Now, using this PID response, one can also directly extract the DEDX. So, in basically this in TPC, we do this particle identification by measuring this DEDX, and this n sigma is basically the difference between the theory DEDX curve from the experimental measure DEDX value by the DEDX resolution. So that is basically the number of sigma. That one can also use their analysis, or one can also directly use this DEDX in their analysis. And this DEDX information one can get by just calling the get TPC signal. Now, these are the basics PID information for the TPC that one can use in their analysis. Now, let's go to some another detector, TOF. So, in case of another detector like TOF and HMPID, all those case, one can directly call the number of n sigmas TOF or number of n sigmas HMPID. But before calling that, one need to check that if the track has any heat in the detector or not. And one can do it by just checking the status of the track. For example, uh, for that you need to take the you need some additional information compared to the AliESD track, and this additional information you can get from the AliV track. So you just need to create a object of your AliV track, and you already have an object of your AliESD track. Then you need to check if the track has any heat in the top. For that, we generally use two conditions. So the first basic condition, we always take a track which has a length greater than 350. So we basically remove the track which has length less than 350. Then we check the status, and the status one can check by just calling the check PID status, where in the first argument you need to put the detector name, so if you want to check if the track has any heat in the TOF or not, then you need to put the detector TOF. If you want to check this thing for the HMPID, then you have to put the HMPID. And the second argument, you need to put the object for the AliV track. So just remember that these information are stored in the AliV track, not in the AliESD track. So you just need to put the object of the LEV track. Then you will get a status. Then you need to check if the status is okay or not. That you can check by just comparing with the LEPID response k date PID okay. Or one can also do it in a different way. Like one can also check two particular things, that the k top out and k time, which are associated if there is any track that has any heat in the top or not. So you can just check the status of your this alive heat track, and also the status of if you have the top out and that k time information or not. So you can do it by this either this way or this way, and after checking if your track has any heat in the top or not, you can directly go to the you can directly extract the number of n sigmas of drop by just calling the number of n sigmas drop. Now using TOF, one can also get some other information like mass information. So in TOF, we calculate the beta or the time or the velocity, which is generally calculated by measuring the time of flight of the TOF detector. And as you know that this beta is related to the mass of the particle. So using that information, one can always calculate the mass distribution or the mass square distribution of a particle using the TOF information. So how one can do that? One can do that. So here I just show how one can do that. So one can first need to get the momentum from the track, and this momentum information is coming from the TPC. So you can get it by just calling get TPC momentum. Then you check the length of the track. Then you get the start time, means when that means what we need to do, we need to calculate the time of flight of the track. So for the calculating the time of flight of the track, you need a start time and a end time. And the start time you will get from the t0 that start time you will getting like this means from the top response from the PID response, you can also get the start time, and you also get the end time by just calling the top signal. So this get top signal will basically gives you a time, that is the time when the track hit at the top. And by subtracting this time from the initial time, you will get the time you will get the travel time of a track. Then you just use the formula that p square by top root over p square by this top time square. But means you can use this just this formula, you can just derive it by using some simple relativistic kinematics, and it will basically gives you the mass square of the particle. So in order to get the mass square, you need two information. One is the momentum, which we will get from the TPC, and another is the time information, which you will get from the top by using the PID response. So the PID response will get the initial start time, and if you get the top signal, it will give you the end time, and just subtracting it, you can get the time of travel, which you can use and calculate the mass square. So one can use this mass square distribution and this TPC and sigma and top and sigma distribution to identify different particles like pion, kaon, proton, deuteron, and others, and use further it in your analysis to get some physical observable. So I will end with this, and in the next two class, I will basically show. Means we will do some hand on experience where we will submit some job with some proper track and event card, and we will try to fill some track variable for some particular type of particle like pion or kaon using some PID information or so. So that's it from my side. So if you have any question, you can ask.
So hello, hello.
Yeah.
So I have a question. Like you explained it earlier, but just I missed it. So for removing the outer bunch pileup, we need a hit just in a SPD, just at least one hit in SPD.
Yeah,
So
one
how
hit
it
in SPD.
and so how it is working? Like just one hit in SPD is removing the outer bunch pileup.
Okay, so it will remove the out of bunch pileup, but I mean the most of the out of bunch pileup, not the all. So this SPD has a readout time of, for example, a readout time of 300 nanosecond, and if you divide it with the branch spacing, which is 25 nanosecond, you can see when you trigger the event uh, with the SPD at that time, if you divide this 300 by 25, you will get only the 12. So at that time, you can have the information from the neighboring 12 branch. Okay. So if did you understand?
Yes, 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 yes.
Okay. So if you have, then you have the information from the neighboring 12 branch. So you cannot remove if there is any track coming from the pileup on this neighboring 12 branch. You cannot remove it by using this any hit in SPD. But you can remove the tracks that are coming from the other branches out from this SPD readout time zone. So
Oh,
if there is any track that is coming from the other branches out of this SPD readout time zone, uh, so it means your detector readout with the SPD will complete until that track reaches to the SPD or not, because your branch is outside from the TPC from the SPD readout zone.
okay, okay, I get it. And another one, I just want to know, just once we require that minimum number of here only in this page only. So sometimes we use like minimum number of clusters TPC, and sometimes we use minimum cross flow TPC. So why it is like that? This
Okay, so it means basically for the run 2 we always recommend to use the cross rows, but in run 1 we generally use the cluster. So it depends on the means if you plot the like stack information, for example the phi distribution, okay, using some TPC cluster cut and TPC cross rows cut, uh, it is much means the homogeneity of this phi distribution is you can get it much better with this TPC cross rows compared to the TPC cluster.
okay,
And there are other also means observe means other also track variable means one can look and see which of these cut is doing the better job, cluster or cross rows. So after Means doing all those studies, it was recommended to use this TPC crossroads in the case of run 2 data. For run 1, one can use this cluster cut. But I think it means it does not have much difference. Means it will, one can do it, put it as in systematic uncertainty. You will not get much difference if you will get, if you use this cluster or crossroads.
Thank you.
Hello. So, Saurabh, you are done, right?
Yes, yes.
Okay. Thanks, Saurabh, for this talk. And before